Welcome to our projectile motion tutorial. In this video, we're going to understand how objects move when they're thrown, shot, or launched into the air and follow a parabolic path under the influence of gravity. Whether it's a basketball being thrown, a cannonball being fired, or even a car jumping off a ramp in an action movie, projectile motion describes it all. Let's dive in. Let's start with some real-world examples to better understand projectile motion. When you throw a basketball, it follows a curved path through the air before either reaching the basket or falling to the ground. Similarly, when a cannonball is fired, it travels in a parabolic path before hitting its target. Even when a car jumps off a ramp, its motion in the air is governed by the same physics. All of these examples demonstrate projectile motion, the path followed by an object when the only force acting on it is gravity. Let's set up a basic scenario to understand projectile motion more formally. Imagine we're launching a ball from the ground at a certain angle with an initial velocity. We'll place this at the origin of our coordinate system. The ball has an initial velocity v0, launched at an angle theta with the horizontal. This initial velocity can be broken down into two components, a horizontal component and a vertical component. The horizontal component is v0 times cosine theta, and the vertical component is v0 times sine theta. Now, let's explore the key assumptions and equations governing projectile motion. The main assumption is that the only force acting on the object is gravity, which means we're neglecting air resistance. In real-life scenarios, air resistance can significantly affect the trajectory, but for our introductory analysis, we'll ignore it. Gravity acts downward with an acceleration of approximately 9.8 meters per second squared, which we denote as g. In the horizontal direction, there is no acceleration since gravity only acts vertically. This means the horizontal velocity remains constant throughout the motion. In the vertical direction, the object experiences a constant downward acceleration due to gravity, which affects its vertical velocity and position over time. Let's derive the equations of motion for both the horizontal and vertical components. Now that we have our equations, let's analyze the trajectory of a projectile. The path of a projectile is a parabola, which comes from combining the horizontal and vertical motion equations. If we eliminate time between our x and y equations, we get a quadratic relationship between y and x, which is the equation of a parabola. Y equals x times tan theta minus g times x squared divided by 2 times v0 squared times cosine squared theta. Let's visualize how the projectile moves over time. Notice that the horizontal component of velocity remains constant, while the vertical component changes due to gravity. At different times, the projectile is at different positions along the parabolic path. The horizontal position increases linearly with time, while the vertical position first increases and then decreases due to gravity. Let's now look at some key parameters and properties of projectile motion. The range is the horizontal distance traveled by the projectile. For a projectile launched from and landing at the same height, the range is given by r equals v0 squared times sine of 2 theta divided by g. The range reaches its maximum when sine of 2 theta equals 1, which occurs when theta equals 45 degrees. The maximum height reached by the projectile is given by h equals v0 squared times sine squared theta divided by 2g. This height is achieved at exactly half the time of flight. The total time of flight for a projectile launched from and returning to the same height is t equals 2 times v0 times sine theta divided by g. Let's solve an example problem to apply what we've learned. A soccer ball is kicked with an initial velocity of 20 meters per second at an angle of 30 degrees with the horizontal, assuming no air resistance and taking g as 9.8 meters per second squared. Find A, the maximum height reached. B, the range horizontal distance traveled. C, the time of flight. Let's start with the maximum height. Using the formula we derived, h equals v0 squared times sine squared theta divided by 2g, substituting our values. H equals 20 squared times sine squared of 30 degrees divided by 2 times 9.8. H equals 400 times 0.25 divided by 19.6. H equals 5.1 meters. Next, let's calculate the range using r equals v0 squared times sine of 2 theta divided by g, substituting. R equals 20 squared times sine of 2 times 30 degrees divided by 9.8. R equals 400 times sine of 60 degrees divided by 9.8. R equals 400 times 0.866 divided by 9.8. R equals 35.3 meters. Finally, for the time of flight, T equals 2 times V0 times sine theta divided by G. Substituting, T equals 2 times 20 times sine of 30 degrees divided by 9.8. T equals 40 times 0.5 divided by 9.8. T equals 2.04 seconds. Let's summarize what we've learned about projectile motion. Projectile motion describes the curved path of an object that is subject only to the acceleration of gravity plus an initial velocity. The key to understanding projectile motion is separating it into horizontal and vertical components. The horizontal velocity remains constant, while the vertical velocity changes due to gravity. We've derived formulas for important parameters. Range, R equals V0 squared times sine of 2 theta divided by G, with maximum range occurring at a launch angle of 45 degrees. Maximum height, H equals V0 squared times sine squared theta divided by 2G. Time of flight, T equals 2 times V0 times sine theta divided by G. These principles have numerous real-world applications from sports to ballistics, and understanding them is fundamental to physics and engineering. Thank you for watching this comprehensive guide to projectile motion.